What's up? My name is Matthew, and in this video we're going to talk about inverse trigonometric functions. For my students, this is Chapter 4, Section 7, and this is going to be an interesting section. This is an interesting topic, and let me preface this by saying that if you don't already have a good understanding and maybe have committed to memory what the graphs of the sine, cosine, and tangent functions look like, if you haven't already committed to your memory what those look like, this section is going to be more difficult. We're going to be referencing, by we I mean I'm going to be referencing very frequently the graphs of those original three functions, but then I've got to keep going. So I'm going to be reflecting those graphs over the line y equals x. I'm going to talk about their domain and their range, and then I'm going to restrict their domain and their range. So maybe even alongside of your notebook or whatever, make sure that you have a little table perhaps of what the domain and the range of the sine, cosine, and tangent functions are, maybe a sketch of what those graphs look like, or not just a sketch, maybe a really nice diagram or something from your previous notes so that you can reference those. At some point in time, you won't be able to reference those, but if you need that crutch at the moment, use it, but be aware that in the not too distant future, like an hour from now, I'm going to hope that you start transitioning away from those as you get a better understanding of those three original functions, their corresponding graphs, and then what I'm going to talk to you about in this section, the inverse trig functions. All right, so let's get over and have a look at those. The properties of inverse trigonometric functions. There are about 10 things I wish I could tell you all at the same time that would make this process a lot easier. But first, let me start out by saying that only one-to-one functions have inverses that are functions. And I'm using the word function very specifically, like passing the vertical line test, that kind of a function. So only one to one functions have inverses that are functions. And if you have two functions that are inverses, for example, here's an inverse function of f, and here's the original function f, and they're operating on x, or the original function f could be operating on the inverse function, which is operating on x. If those two functions are indeed inverses, then they're going to cancel each other out, just like squaring and square rooting, and you'll be left with just the original value, which in this case is a generic variable, x. Visually, graphically, the graphs of f and f inverse are reflections of each other through the line or over the line y equals x. Now, when you have, let's see, 1, 2, 3, 4, 1, 2, 3, 4. Let's just look at this graph real quick. I'm going to plot the point 1, 4. 1, 4. And then I'm going to take the x and y coordinates and switch them. I'm going to swap the x and the y, and I would get 4, 1, which is out here. 4, 1. So what? And this isn't the most accurate graph I've ever drawn, to be sure. However, what I'm trying to point out here is, let's see how well I can do with this. Yeah, it's not my best illustration. But what I was hoping to do, but I was a little cavalier in my diagram, is to illustrate, which is now failing miserably, that these 2 points are reflections of each other over the line y equals x. So, I would have much preferred to have 4, 1 actually be in the correct location. Can I fix it somewhat gracefully? Let me see if I can. Just bear with me one moment, and this is going to be 4 right here, so this will be 2 and 1 and 3, and this little mark here that describes the location of 1 was a little low, so let's bring that up just a smidge, and then we can put, oh, there it is. There's 4, 1. 4, 1. I should have pre-drawn that, obviously. Notice that those 2 points are reflections of each other over the line y equals x. Y equals x. I swapped the x and the y values. X and y, domain and range. Now, it's like I've swapped the domain and the range. All of the x values and all of the y values. The result is an image that is a reflection over the line y equals x. That's important because in this section we're going to be working with inverse functions, and their graphs of each other will be reflections over the line y equals x. Now, inverse sine and cosine functions, let's get a little bit more specific. Not just generic, general inverse functions, but specifically sine and cosine. What you're seeing here are the graphs of the sine and cosine functions. What it says underneath those is how can we restrict the domains so that the sine and cosine functions have inverse functions. In other words, inverses that are functions. Inverse graphs that would pass the vertical line test. If you're familiar with the horizontal line test, you can look at these 2 graphs and see that they clearly fail the horizontal line test, which means these graphs would not have inverses that are functions. So what we're going to do is, and let me use a highlighter I think for this. What we're going to do is we're going to restrict, and we're only going to use part of the sine function that goes from negative pi over 2 to positive pi over 2, including the endpoints, so with square brackets. And for cosine, a little different, we're only going to use this part, which goes from 0 to pi in the x direction, including, with square brackets, the 0 and the pi. The reason we're doing that is so that if we flipped this highlighted portion of the graph over the line y equals x, the resulting graph would still be a function. And I'm going to pause real quick and just do a quick demonstration. You won't even know I'm gone. All right, this is super fancy high-tech stuff that I've done here. I just took a piece of printer paper and I used just a regular marker board Expo marker because those put out a lot of ink. So I knew that it would bleed through this regular copy paper a little bit. And I drew just that middle portion that I highlighted a moment ago, the middle part of the graph of the sine function, and then the parts that I had not highlighted on the, well, similar to what you're seeing. Where is it? It's over there for the cosine function, right? But behind where I am right now was that graph of the sine function. So I took just the middle part of the sine function and I drew it with this Expo marker on the paper so that it would bleed through. And then other than the part of the graph that goes from negative pi over 2 to pi over 2, I did that just with a dotted part of the curve. So this is the restricted part of the sine function that we're going to be working with when we talk about the inverse sine function. In order to graph the inverse, you have to reflect this solid curve, not the dashed part, although we're going to reflect all of it. You want to reflect the solid part of this curve over the line y equals x. That's difficult to do. I tried to draw 1 point, 1, 4, and flip that over the line y equals x, and you saw how well that went. So what I did is I drew this image, and then I'm going to take this piece of paper, and I'm showing you this because you can do this too if it helps you to get a better understanding. If you take the paper, right, so I've got my paper long ways, and I'm going to flip it diagonally so that now it's in landscape, and so that I can still see around my piece of paper. I'm folding it in half. You don't have to do that part. And now what I have, this is the inverse sine graph. I'm trying to get it in focus. There we go. And you'll notice that the solid part of this curve, just the solid part, does pass the vertical line test. So that part is a function. But if we included the dotted part of this curve, it would not pass the vertical line test. We'd have this, this wavy line that goes all the way up and all the way down to positive and negative infinity. Would very much not pass the vertical line test. So that's why we're restricting the domain. It's so that when we switch the domain and the range, in taking the inverse of this particular trig function, the sine function, we end up with a function that has a graph that's still the graph of a function. You can do this same process with the cosine function. And actually, when I drew this initially on this side of the paper with my expo marker, and then I flipped my paper over diagonally, before I showed it to you, I did, it didn't bleed through exceptionally well, but well enough that I could see it. And then I was able to use the expo marker on the back side of the paper and sort of trace the part of it that bled through so that I could see it really well. All right, where are we now? Put me back in the corner, make me small again. There we go. Okay, so that's just a little bit more about why it is that we're, maybe not why we're doing what we're doing, but a little more about what we're doing. So you can actually see the process of taking the inverse in motion. So I mentioned that we have to restrict the domain and the range. Let's see what those actual values are. I left the door open for the cats, but they still feel the need to push it open. So the restricted sine function has a domain that goes from negative pi over 2 to pi over 2. Oops, that's a square bracket there, both of those. And the range, as you can see in this diagram, the graph on the left goes from negative 1 to positive 1, inclusive. And the inverse function, when we flip the paper diagonally, when we swap the x and the y values, literally the domain and the range are trading places. So the domain of the inverse sine function goes from negative 1 to positive 1, and the range from negative pi over 2 to pi over 2. Square brackets on all of those, please. The cosine function, let's glance at this graph. The part that I highlighted from left to right in the x direction goes from 0 to pi. Vertically, it goes from negative 1 to positive 1. Always least to greatest, left to right, bottom to top. So the restricted cosine function, inclusive, we said is going from 0 to pi, and the range goes from negative 1 to positive 1, and then swap the domain and the range again as we take the inverse, this time of the cosine function. The inverse sine function, there's a little spot on the bottom of our page to describe notation. We're just going to keep going and we're going to see it. Highlighted in blue here in the principal notes, you see inverse sine function. So this notation, it looks like sine to the negative 1. We don't say that. We say sine inverse or inverse sine. You might see it written as arc sine. 6 letters, A, R, C, S, I, N, all written like one word, arc sine, arc cosine, arctan, synonymous with inverse. But for the most part, we're going to see it with this sort of exponent of negative 1. Now, if you really wanted to apply the traditional exponent of negative 1, you would have to wrap the sine function in parentheses and put the exponent of negative 1 on the outside. That would cause you to take the reciprocal of the function, not the inverse. And the reciprocal of sine, of course, is 1 over sine, which we call cosecant. So there's notation for you. Let's jot this down so that we can refer to this later. So in the left-hand column, those are theta values, in other words, x values. In the right-hand column are going to be our y values for the graph of the sine function, from negative pi over 2 to pi over 2, because that's the part of the domain that we're going to be working with. The sine function will start at negative 1. It will come up to negative root 3 over 2, and then negative 1/2. And what's wrong with that? Negative 1, negative root 3. Oh, sorry. I jumped the gun. Ugh. Get rid of this. Negative pi over 6 is going to be negative 1/2. This is going to be negative root 2 over 2. At 0, we're still crossing through the origin, and then we move into the sort of first quadrant results that we're used to. At pi over 6, the sine function equals the positive 1/2, and then positive root 2 over 2. At pi over 4, then root 3 over 2, and finally positive 1. Okay, opposite over hypotenuse. Yes, looking good. Let's go through that same process for cosine. Notice the left-hand column here is different because we're going from 0 to pi. It's a different restricted domain. Cosine starts out on the y-axis at its maximum, so 0, 1, and then it starts descending. We go to root 3 over 2, and then root 2 over 2, this, and then, then the 1/2, and 0, so we're then crossing the x-axis, and then we get the negatives of those, negative 1/2, negative root 2 over 2, negative root 3 over 2, and finally negative 1 at pi. We hit the minimum. And you can compare those to the graphs that were just above. So we can use this as reference. You might want to use that as reference as you're taking some inverses. I don't have any notes for you. These are all notes. All right, so what's the what is 3 squared? That's 9. And what about the square root of 9? That's 3. So squaring takes you from the domain to the range, and square rooting takes you from the range, the 9 value, back to the domain. This is the original function. This is the inverse function that takes you back where you came from. Okay, so one goes forwards, one goes backwards. That's a way that we could look at it. Sometimes that works very nicely. Not always, unfortunately. And we're going to get into that, I think, right after we finish talking about the tangent function. So following this 3 squared equals 9, root 9 equals 3 conversation, if the sine of pi over 4 equals root 2 over 2, if that's going forwards, right, from the domain to the range, if that's the original function, and now we're working with the inverse function, and we're going from the range, that's a negative 1 there, fix that. Now we're going from the range back to the domain, domain to range. Range should go back to domain. So this should be a pi over 4. And guess what? It is. I love it when things work the way they're supposed to. Now, the sine of 3 pi over 4 is also equal to root 2 over 2. Can you tell what the problem is? If this is the function going forwards, then if I take the inverse sine of root 2 over 2, shouldn't that take me back to 3 pi over 4? You'd want it to, but it doesn't. The inverse sine of root 2 over 2 takes you to 1 pi over 4. It doesn't take you back to 3 pi over 4. So we're going to have to contend with that, and we're going to be doing that at some length in this video. But first, let's talk about the inverse, it does say inverse back there, inverse tangent and cotangent functions. What you're looking at here are the tangent and cotangent functions, not the inverses. The part of these graphs that we're going to focus on, when we restrict the domain, we're going to focus on this part of the tangent function that goes from negative pi over 2 to pi over 2. And when it comes to cotan, we're going to focus on this part of the cotangent function that goes from 0 to pi. That answers the question of how can we restrict the domains so that the tangent and cotangent functions have inverses that are actually functions. So let's fill in this table with those restricted domains and ranges. We just said that the restricted tangent now goes from negative pi over 2 to pi over 2. This is a little bit different than the sine or cosine because in the tangent graph we have asymptotes. So the domain will have parentheses and exclude those two values. The range here for the tangent function is also unique because it goes from negative infinity to positive infinity. The inverse tangent function, we do indeed still swap the domain and range. going from negative to positive infinity, and here going from negative pi over 2 to pi over 2. Still with parentheses. I highly recommend that you go through that process of using a piece of copy paper or printer paper and a very heavy marker like an Expo marker and sketch, including the asymptotes for the tangent function. Please do yourself a favor, draw that. There's no substitute for watching me go through that process. Take another piece of copy paper, sketch that thing onto it, heavy-handed with the marker so that it bleeds through a little bit. Maybe put another piece of paper under it so it doesn't bleed onto your desk or your notebook or whatever. And then flip it diagonally so that you can see what happens when the domain and the range trade places. This graph goes all the way up to positive infinity and all the way down to negative infinity. When you flip that thing over the line y equals x, it's, instead of it looking like a vertical column, it's now going to look like a horizontal band sandwiched in between negative pi over 2 and positive pi over 2, but going infinitely far in the horizontal directions. So it's a drastic, very drastic difference in graphs. I would do that if I were you, at the very least just for the tangent function. Restricted cotan. Have a look at this graph. We said that the domain goes from 0 to pi now. Oops, that's the highlighter still. 0 to pi. Asymptotes are there, so we're using parentheses. Negative infinity here. That's a very tall graph. And the inverse, swap the domain and the range. Parentheses all day. So we're seeing this notation again. This is that very generic idea behind how functions and inverse functions interact. Like squaring and square rooting, ideally they cancel each other out. Trig functions are a little weird, so they don't actually always cancel each other out. Sometimes we have to do a little bit of preliminary work in order to allow them to cancel out. That's one scenario. Well, maybe there are three scenarios. One, it works exactly as it's supposed to. They just cancel each other out, and the result is the x value. Sometimes we're going to have to do a little bit of preliminary work in order to allow the function and the inverse function to cancel each other out. And thirdly, sometimes it's not going to work. There's no modification that we can make in order to allow the functions to cancel each other out. In your notes, and when you review for an exam, you should make sure that in your exam review notes, which might be a consolidated version of your regular lecture notes, make sure to include an example of each three of those instances so that you know what potentials to watch out for on an exam or on a quiz. Now this is a great table, and I'm not going to put the whole thing on the screen at once, I don't think, because it's kind of a lot. But look here. The sine and the inverse sine function are operating on x, and it looks like they've canceled each other out, and we get only the x. Does that happen all the time? It does not. It only happens when your x value is in the interval from -1 to +1. Where'd that -1 and +1 come from in the square brackets? This is, if this were organized in a column, it's not much of a column anymore, is it? These values over here, oh, and it stops right there. I guess I have all of it on the screen after all. The values to the right of that blue pseudo line that I just drew are the domain of the inner function. And by inner function, I mean this one, and 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 this one. The ones that are inside those parentheses. Those are the inner functions. This stuff over here, and this, those are the domains of those inner functions. Put a note in your notes so that you know how those match up. Let's just look at one example. What's the domain of the inverse sine function? I bet it's from -1 to +1. Inverse sine function, domain, -1 to +1. How am I supposed to remember that? Great question. The domain of the inverse sine function is the range of the regular sine function. How am I supposed to remember that? If you knew what the regular sine function looked like, you'd be able to tell what the range is, because it's a curve that comes out of the origin and goes up to the, I guess I have to go this way, goes up to its maximum at 1, comes down, and then eventually to its minimum at -1 before coming back up to 2 pi. See how important it is to have those images of the original trig functions in your mind? We're going to use them a whole bunch right now in a handful of example problems. All right, let me fly down to wherever we were down here. So that was just one example there. Oh boy. Now I'm all over the place. Okay, we're back. Sorry about that. So I'm not going to read through this table, but we need to be sensitive to the domain of the inner functions. All right, let's see some examples. The first one that's up here says the cosine of the inverse cosine of 2. Don't just knee-jerk reaction. They cancel out. The answer is 2. Not necessarily. What's the domain of the inverse cosine function? Train yourself to go through this thought process. You could even write out this thought process. I wouldn't hesitate. I'm not going to hesitate. I recommend that you grab a separate sheet of paper, lined paper even maybe, write down this problem, and write out the thought process, the decision-making, investigative process about how we come into a conclusion in order to answer this question. I look at this question, and the first thing I ask myself is, what's the domain of the inverse cosine function? Because if 2 is not in the domain of the inverse cosine function, we're done. This problem is a non-starter. Now, I'm also training myself to prepare for a quiz and then eventually an exam, so I want to come up with a way that I can answer this domain question about the inverse cosine function without having to refer to my notes. What's the domain of the inverse cosine function? The domain of the inverse function is the same as the range of the regular function. What's the range of the cosine function? And then I picture the cosine function, or I draw a quick sketch. The range of the regular cosine function goes up to +1 and goes as low as -1. So the number 2 is not in the range of the regular cosine function. Therefore, the number 2 is not in the domain of the inverse cosine function. Therefore, this question cannot be completed. There is no solution. I haven't written anything down. I just talked through that. Rewatch that, re-listen to that explanation, and see what you can do about taking some notes using your own words and your own description of that thought process. Step 1 maybe was domain of inner, which in this case was the cosine inverse function. I ran out of space, so I'm writing function. And there needs to be a question mark at the end of that. What's the domain of the inner inverse cosine function? And then I said domain of cosine inverse is the range of the cosine function. And then I imagined the cosine function. So third, I thought, what does the cosine function look like? Well, 1 period worth of the cosine function looks like this. And the top of it right here is at +1 and the bottom's at -1. So the range goes from negative to +1. Range -1, +1. And then I looked at the 2. I looked at the argument in the actual problem that we're working on, and I notice that 2, now check out this notation. It's like a C with a little line in it, right? We've seen this notation once before. Is a member of is how you read that symbol. Maybe this middle line's a little bit longer. 2 is not a member of the range that goes from -1 to +1. Therefore, if you want to do an arrow, or you can write therefore, no solution. Now we're going to do another problem, and the input value is not going to be in the restricted domain of the inner function, and there's still going to be a solution. You're hating me right now. Don't blame me, I'm just the messenger. Come over here with me. Inverse cosine of the cosine. Now check this out, the inner function is the regular cosine function, not the inverse cosine function, okay? These are different problems. Let's go through pretty much the same process. What's the domain of the inner function? Step 1, what's the domain of the inner function? What's the domain of the restricted cosine function? Zero to pi is the domain of the restricted cosine function, so that if you took your piece of paper and you flipped it diagonally, the resulting graph would still be a function. What was step number 2? Domain of... Oh, we don't really have to ask ourselves question number 2 because the cosine graph is the one that we're already familiar with. So can we skip to step number 3? Well, we can really go to step number 4. Step number 4 says, or allowed us to notice, that 7 pi over 6 is not a member of the domain which is going from 0 to pi. Therefore, no solution? No. We still have some options here. In this problem, we have options because 7 pi over 6 is an angle measure. The cosine function operates on angle measures. That's what we've been doing for a couple of weeks now, right? Trig function, tangent pi over 4, cosecant 11 pi over 6. Trig function, angle measure. That's what we've got here, cosine 7 pi over 6. We know that the period of the cosine function is 7 pi over 6. Therefore, we're going to try to modify this angle measure. Since the period of the cosine function is 7 pi over 6, I note that the cosine of 7 pi over 6 is equal to the cosine of 7 pi over 6 minus 2 pi, which if you use a common denominator, which is 7 pi over 6 minus 12 pi over 6, this turns into the cosine of negative 5 pi over 6. A different angle measure. Maybe this angle measure is in the domain of the restricted cosine function. But negative 5 pi over 6 is not a member of the restricted domain that goes from 0 to pi. So we're going to modify the angle again. Isn't this fun? Remember that cosine is an even function. Cosine is even. Therefore, that's an arrow, therefore, the cosine of negative 5 pi over 6 is equal to the cosine of positive 5 pi over 6. Are you jumping up and down? Are you ecstatic right now? Can I slide this up right now? There we go. I'm ecstatic. because 5 pi over 6 is in the domain, the restricted domain that goes from 0 to pi. Therefore, now I wish I had a little bit more space to write another line below where I'm at right now, but instead I'm going to go across the bottom of the page. I'm going to rewrite the original problem. Therefore, cosine inverse of the cosine of 7 pi over 6 is equal to the cosine inverse of the cosine of positive 5 pi over 6. And you could verify that for yourself. Draw a couple of diagrams, speed quiz style. And since 5 pi over 6, which is what that says, believe it or not, since 5 pi over 6 is in the domain of the restricted cosine function, the inverse cosine and the cosine can cancel out, leaving us just with our x value, or you can think of it as a theta value, our input value, and that becomes our answer. Now in this problem, we were able to modify our angle measure twice. We modified the input that was going into our inner function. Why didn't we do that in the first problem that we just did? Isn't there something we could add or subtract to this? No. Why not? Because this number 2 right here is not an angle measure. That 2 right there is, because we're working with cosine, that 2 right there is adjacent over hypotenuse. That really says 2 over 1. And there's no way the adjacent side can be longer than the hypotenuse, 2 over 1. So that 2 is really representing a triangle that can't exist. And there's no modifying the side lengths of that triangle, which is why that problem ended up being a non-starter. How do I know that this is really representing side length divided by side length? How do I really know that that's a 2 over 1? Because while regular trig functions operate on angle measures, inverse trig functions operate on unitless values, side length divided by side length. Even if this 2 that's inside of here were written as 2 feet over 1 foot, the units would still cancel, right? It's still a side length divided by side length. It's still adjacent divided by hypotenuse. And the units cancel, which is why I called it a unitless value. So again, regular trig functions operate on angle measures. Inverse trig functions operate on unitless values, which are derived from a side length being divided by a side length according to SOHCAHTOA. If that doesn't sound like we're speaking a foreign language, I don't know what to tell you. It's a little slice of madness. If you need to take a break, get something to drink, get your blood sugar up, take a quick walk around the block, get a little sun on your face, come back and tackle these. So we're going to do some more practice right now. I'm going to have, all these are time stamped in the description of this video. So if you want to jump back to each one of these individually, go into the description and you can click on the hyperlinked times that are there. In this first problem, we're working with just an inverse trig function, which is good. We need to do that. And I just finished saying that the inverse trig functions operate on unitless values, and that those unitless values come from SOHCAHTOA, which is side length divided by side length. So what's really happening here is that the inverse tan is operating on either -1 over +1, or maybe it's +1 over -1, but it's definitely, I'm going to put it up here, This is opposite over adjacent. It's the tangent function. So now what am I supposed to do? Well, maybe we should take note of, let's check in with the domain of the restricted tangent function. Can we even do this problem? Domain of tan inverse is range of the regular tangent function, which is, I'm really scribbling these notes, but I'm saying it out loud, so write down what I say. Don't try to copy down what I'm writing. If you need subtitles, turn on subtitles. What's the range of the original tangent function? Oh yeah, that's the one that goes curving from negative to positive infinity. Negative 1 is in negative infinity to positive infinity. Negative 1 is a member of the domain of the inverse tangent function because negative 1 is in that list of numbers. So we're good to go. You can put yay, check mark, smiley face, or some sort of longer description of why we're happy, and we get to proceed. Okay, so now what am I supposed to do? The domain of the inverse tangent function is all of these numbers. What's the range of the inverse tangent function? The range of the inverse tangent function is the domain of the restricted regular tangent function, which lives between those two asymptotes, negative pi over 2 to positive pi over 2. So the answer that we're going to get out of this inverse tangent function needs to be between negative pi over 2 and positive pi over 2. Note that the range of tan inverse is the domain of restricted tangent, which is, with parentheses, please, negative pi over 2 to positive pi over 2. I'm not going to write all of this out every time because it's time consuming and really we need to be using this real estate for some other stuff, which I'm going to get to in a moment. But for this one, I'll give you one more talk through on that thought process so that you have it. So again, our answer to this question is going to be between negative pi over 2 and positive pi over 2. Where is that? Well, 0 is here, and negative pi over 2 on the unit circle is down here, and positive pi over 2 is due north on the unit circle. So we're going to be getting an answer that's in the fourth or first quadrant? Is that true? It's true. Our answer is going to be an angle measure that's in the fourth or first quadrant? Yeah. You know, if I took the tangent, for example, of an angle measure like pi over 4, the answer would be root 2 over root 2, which is equal to 1. So let me replace that with a 1. I took the tangent of an angle measure and I got a unitless value. Remember that the inverse tangent takes us back where we came from. It takes us from the unitless value back to the angle measure. So the output of an inverse trig function is an angle measure. Regular trig functions go from angle measure to unitless value. Inverse trig functions go from unitless value back to an angle measure. So our answer is indeed going to be an angle measure. Could I draw this angle measure? Absolutely. I need to draw an angle such that the tangent of that angle equals -1. That's true. And I'm pretty sure that happens down here. I like to use the hypotenuse of 2. I'll even go so far as to make that look like the number 2. There you go. Which makes this a -√2 as the opposite side and the adjacent side as a +2. And this is an angle measure of -π/4. The reference angle we would say is +π/4, but the actual location on the unit circle can be described as -π/4. I'm describing it as -π/4 because -π/4 is in here. It's between -π/2 and +π/2. I'm not describing it as 7π/4. While that is the same location, 7π/4 is literally not between -π/2 and π/2. So that's why I'm not describing it that way. So the answer to my question, the inverse tan of -1 is -π/4. Just sit with that for a minute. Go back through this process. Now again, I made this a very labor-intensive process, but it works. I wrote down all the thought process and investigation, or at least a lot of it. I made sure that the -1 going into the inverse tangent function was even a possibility, and I confirmed that -1 is in the domain of the inverse tangent function. And then I thought, well, what am I going to get out of that inverse tangent function as an answer? So I looked at the range of the inverse tangent function, and I noted that it goes from -π/2 to π/2. And then I drew a little illustration of where that is. -π/2 to π/2 is somewhere in the fourth or the first quadrants. So my answer is literally going to appear in one of those two quadrants. And then I actually drew the triangle that corresponds to the angle measure such that the tangent of that angle measure is -1. That -1 right there, this one. I drew a diagram of a triangle in one of my optional quadrants, which ended up being the fourth quadrant. I drew an angle in one of my optional quadrants such that the tangent of that angle measure equaled -1. And then the angle measure was my answer. You figure out how to write out the steps for that, okay? You can look in the ebook and see if there's a different way to march through that process or describe the thought process. That one's kind of a tricky one. There are some tricky ones out there. Okay, let's go to the next one. Inverse cosine 4π/3. What's the domain of the restricted cosine function? Cosine. Domain. I'm picturing it. I'm picturing the original cosine function. I'm picturing the thing that I drew on the paper with the marker that I was flipping over diagonally, the thing that Newbeck highlighted 3 pages ago, whatever it was, that portion of the cosine graph. Oh yeah, that went from 0 to pi. Is 4π/3 in this restricted domain? No. 4π/3 is not a member of this domain. So, modify the angle. The cosine of 4π/3 is equal to the cosine of 4π/3 minus 2π. That's a move that we've used before. Okay, so that's equal to the cosine of 2π is 6π/3. 4π/3 minus 6π/3 is -2π/3. Negative 2 pi over 3 is, I guess I can write that out. Negative 2 pi over 3 is not a member of the domain that we're working with that goes from 0 to pi. So I'm going to modify my angle measure again. The cosine of negative 2 pi over 3 is equal to the cosine of positive 2 pi over 3. Because cosine is an even function, I didn't write that down this time. If you need to write it down, you write it down. 2 pi over 3 is in the domain, is a member of 0 to pi. That needs to be a square bracket. Therefore, and then you can write all of it out again. You can write out that the cosine inverse of the cosine of 4 pi over 3 equals the cosine inverse of the cosine of 2 pi over 3 equals 2 pi over 3. Because once this 4 pi over 3 becomes a 2 pi over 3, the cosine and the inverse cosine are going to finally cancel each other out, leaving you with your final answer of 2 pi over 3. Nice one. All right, let's do this next one a bit faster. We know that 3 pi is not in the domain of the original cosine function. I'm going to write simply that this is equal to the cosine inverse of the cosine of pi, which is equal to pi is in the domain, so the inverse cosine and the cosine can cancel out, leaving us with a final answer of pi. So it's only with that deeper understanding of this process that you can rip through that logic super fast and get your answers in much less time. In the next problem, the 3 pi is still there, except the inner and outer functions have swapped places. Let's make an actual note this time that says that the domain, let me switch colors back so that we still have a sort of a difference between problems here. The domain of cosine inverse is the range of the original cosine function, which goes from -1 to +1. 3 pi is not in that domain, therefore no solution. Why didn't I modify the 3 pi? Isn't 3 pi an angle measure? 3 pi is a number. It becomes an angle measure when you put it into a trig function. In this case, I'm not putting it into a trig function. I'm putting it into an inverse trig function, which means that 3 pi is 3 pi over 1. It's 3 pi feet divided by 1 feet. It's adjacent divided by hypotenuse, and you can't have an adjacent side of 3 pi, which is bigger than the number 6, divided by a hypotenuse of 1. Your adjacent side cannot be larger than your hypotenuse. So this one's a non-starter. The inverse tan of -pi over 3. Check this out. I now know from having done a previous problem that the inverse tangent function is going to has a domain that's infinite, from negative to positive infinity, so I don't have to worry about the input value being out of the domain. Inverse tan is like ready to rock and roll. And I remember from a previous problem that the range of the inverse tangent function, my available output values, are between -pi over 2 and +pi over 2, which is either in the 4th quadrant or the 1st quadrant. And I'm going to be drawing a diagram of an angle measure such that the tangent of that angle measure is negative root 3. And the tangent function is only going to be outputting a negative angle measure, or sorry, a negative answer in the fourth quadrant, or the second quadrant, but we're not working with the second quadrant. So for sure, my diagram is going to be in the fourth quadrant. And I need opposite over adjacent to equal negative square root of 3 over 1. Well, if the opposite side is root 3, that's the long side. The adjacent side is the 1 as the short side. So this one's a 1 and this one's a root 3. The root 3 is below the x-axis, that's negative. And the 60-degree angle, or pi over 3 radian measured angle, is across from the side length of root 3. Therefore, my theta value is equal to pi over 3, but it's been rotated down from the positive x-axis, so it's an angle measure of negative rad 3, or sorry, negative pi over 3. And that's your final answer. There are other ways to explain this topic. I'm going heavy on making sure that you're familiar with the domain and the range of the original trig functions so that you can then restrict those and then have them trade places, the domain and the range, so that you're now working with your inverse trig function. And then I'm still falling back on my diagrams and my knowledge of 30, 60, 90 triangles and 45, 90, 45, 45, 90 triangles so that I can draw a diagram and get to an answer. So it's a good thing that we're so good at drawing sketches of these different situations, because here we definitely want to solve this problem using a sketch. The inverse sine function has a domain that's the same as the range of the regular sine function, which goes from -1 to +1. 5/13 is in that interval from -1 to +1. Domain of inverse sine is -1 to +1. 5/13 is a member of that domain. So proceed. And what am I going to proceed to? Well, now I'm going to contemplate the range of the inverse sine function. The range of the inverse sine function is the domain of the restricted sine function, which is just that pink highlighted part of the original sine graph that horizontally goes from -pi/2 to +pi/2. So the range of the inverse sine function is the interval that goes from -pi/2 to pi/2. In other words, quadrant 4 or quadrant 1. So we're going to be drawing a diagram in quadrant 1 or quadrant 4 that corresponds to the sine function, and SOHCAHTOA tell us that the 5/13 represents opposite over hypotenuse. And sine of an angle measure being greater than 0 happens in which quadrants? Ambitious students take calculus. They're all positive in the first quadrant, all the trig functions, and students stands for sine, which happens in the second quadrant. So we're definitely going to be drawing our diagram in the first quadrant. Let's do that. I need opposite over hypotenuse to be 5/13. The missing leg, my b value, or you could call it your a value, or your x value, or your h value. That can be determined using the Pythagorean theorem. And if you go through the motions, I'll write it up real quick. A squared plus b squared equals c squared. C always has to be the hypotenuse. So this is 5 squared plus b squared is equal to 13 squared. And this is a 25. B squared, 169. B squared is equal to 144. B is equal to 12. This is a famous triangle. I already knew what the answer was. It's a 5, 12, 13 triangle. It's one of the Pythagorean triples. The 3, 4, 5 triangle, the 5, 12, 13, the 8, 15, 17, and the 7, 24, 25. Those are the primary Pythagorean triples that we work with our right triangles. Now that I know that this is equal to 12, and we're never actually going to calculate this theta value, but that theta value, if you went into a calculator in degree mode, for example, you could get a feel for what that theta value actually is. Take a scientific or graphing calculator, put it in degree mode, and evaluate the inverse sine of 5/13, and that'll tell you what theta is. I don't actually need to know what theta equals. All I need to know is what theta looks like. And this diagram is what theta looks like. And now I'm going to use that diagram to evaluate the cotan. I'll call it theta. Cotangent, tangent is opposite over adjacent, so this is adjacent over opposite, which is equal to 12 over 5. And nothing, and that's it. Adjacent over opposite. Perfection. Nice job. Reverse engineering those diagrams to then use them in the forward direction to actually evaluate a trig function is a good skill to have. And this problem, if I can pull this off before my battery dies, it's very strange. This software uses enough juice that even plugged in, my battery depletes. All right, let's knock out this last question. The scenario that we're working with here is going to result in an answer that's an algebraic expression because we're taking the inverse cosine of 1 over a variable and not a specific number. So this is a little different. We're definitely on the last page of notes on this one. And let's talk about the domain of the inverse cosine function. Domain of the inverse cosine function is the range of the regular cosine function, which goes from -1 to +1. And we're good there because this problem tells us to assume that x is positive and the inverse function is defined for, it says defined for x, the x variable, and then 1 over x. We're going to assume that it works and that 1 over x is in the domain of the inverse cosine function. Now that 1 over x as an input value into the inverse trig function is a unitless value. Inverse trig functions operate on unitless values, which are the result of SOHCAHTOA, side length divided by side length. Units cancel, so we're left with a unitless value. And in the case of cosine, we're working with adjacent divided by hypotenuse. And we're being told that x is positive. So our adjacent side is a +1, and our hypotenuse is a positive something larger than 1. Or potentially equal to 1, I suppose. Now, what kind of an answer could we get out of the inverse cosine function? In other words, what's the range of the inverse cosine function? You go back to the original graph of the cosine function, and then we restricted that graph. I used my pink highlighter, what seems like ages ago now, and I only highlighted the part of the cosine curve that starts at 0, 1 and moved down and to the right to pi, -1. So the range of the inverse cosine function is the domain of the original restricted cosine function, which went from 0 to pi. The range of inverse cosine, I'm just going to say the range of inverse cosine, I'll even say of 1 over x, is between 0 and pi. This is an angle measure that's between 0 and pi. So when we draw the diagram that corresponds to that angle measure, we're going to be drawing it in either the first or second quadrant, somewhere between 0 and pi. However, cosine is negative in the second quadrant. Therefore, we will be drawing our diagram in the first quadrant. I'm not writing that down. If you need to write that down, that thought process, write it down. I think it's a great idea, because you need some explanation between what I've written so far and what I'm about to write. So I'm leaving you a little bit of space in here. But what I'm about to draw is the diagram in the first quadrant. So theta is in the first, and cosine, we said from SOHCAHTOA, is adjacent divided by hypotenuse, which in this case is equal to 1 over x. So I'm just going to throw this hypotenuse somewhere up into the first quadrant. It's not necessarily a 45-degree angle. That's just roughly where I'm drawing it. But the adjacent side measures 1, and the hypotenuse measures x. And by the Pythagorean theorem, our vertical leg, our opposite side length, is equal to the square root of x squared minus 1 by Pythagorean theorem, THM. And in our diagram, we could sneak in here and put theta. Already, this has been a challenging process for some of you who are watching this. Okay, so maybe rewatch the first part of that process, because without this diagram, there's no way that you can answer the final question, which is to then evaluate the tangent of theta, a theta value that we will never know. We don't know what the actual value of it is. All we do is we know what it looks like because we drew a good diagram. Tangent of theta is equal to opposite divided by adjacent, which in this case is equal to the square root of x squared minus 1 divided by the adjacent length of 1, which simplifies to x squared minus 1 square rooted. And that's your final answer. Boy, did I make that look easy. A lot of stuff happened in this problem. This is one where if you can go onto the web and find another example problem that's similar to this one, that has an answer provided, see what you can do about going through the motions and examining the domain and the range of the inner function, drawing the diagram in the correct place, and then getting yourself a final answer. In an hour from now, you will probably have forgotten this process, so you could redo this problem, and then by tomorrow, surely you will have forgotten this process, so you can try this problem again tomorrow. But this is sort of maybe the ultimate test of being able to go through the motions, knowing the domains, ranges, restricted domains and ranges, being able to switch your domain and range in order to go from your regular trig function to your inverse trig functions. This is an intense topic. Okay, we're late in the chapter, so if you're feeling a little strain, I wouldn't be surprised. All right, that is it for this section. Sophie has come to grace us with her presence. She says, bye. See you next time. Thanks so much.